All right, good afternoon, class. Can you guys hear me online? Do All right, excellent. Okay, so I'm just gonna stop sharing and reshare on Zoom because you take off the notifications. Let's leaving. Let's try again. All right, excellent. Change one, click on the public. Okay, so I'm putting up the stream, and yeah, let's see how we could do this. All right, guys. Good afternoon. So I'm doing this taking this class fully online. Hopefully nobody in lab, but if those in the lab, there may be internet access right now. Because of our transitioning happening, I think they're going to leave utility power as long as possible until we need to do any actual connection. So if you try to connect to any websites, I would have given you a form to fill out to see when systems are going down and stuff, or what is not available. Now that could happen now, it could happen a little later. Not so sure. So you try different times. So chances are it might be working right now, but we do what could happen. So anyhow, so this is where we're looking at. We're looking at span tree protocol and at the channel. So those who have downloaded files might have access to my learning. I think I still have access to my learning easily, so I could stay online. Right. So this is what our span tree and channel design looks like right now. Now, interesting enough, the group project I'm going to put a third group project. So there's going to end up being three. So there's two right now. There's going to be a third one. I'm creating one that looks like this, but a little more complicated. Well, okay, a lot more complicated because I'm going to actually mirror it based on some CCNP designs. So you're going to see it. Yeah, you're going to get confused, but that's what the whole idea is to get, because that's what our enterprise should look like based on Cisco's design. And we'll start to look at that. Now you're going to get all the different protocols, just like what the other groups will have. That's group this third project, not this assignment, this group lab, sorry. So everybody's going to actually get whoever it is in this third project will get this kind of design, maybe more. So what is something called switching blocks. Just put that in here. So this area might end up being here, and this might actually be in a switching block. Might be backbone, so that's a switching block. Called SWB1. There's another switching block here. So what's happening is that distribution on top is really going to change the core. Right? I just digress. I just telling you what group project look like. We'll change the core. And these backbones, another backbone will change the distribution. And we may actually have the distribution will actually be routed devices. So this is where you'll place you'll route the protocols on. And on top here, there's no routing up here. It's just VLAN stuff happening on top. Right. So let me not confuse you too much here, but let's focus on the lab first. And I will erase this. Right. Let me just focus on the lab and then we'll take it from there. Right. So the design, as I would have talked about span tree before, you'll notice some of these ports are actually you see them here, the orange. Now, this is what you would have realized when you guys started up the or opened up the Packet Tracer lab and you looked at this first off Packet Tracer. Let me just open the Packet Tracer lab now. File. Already have. When you load this up the first time, as a matter of fact, I can open it up now again. I'm going to open it up again. See, I'm going to go back up and reopen it. And I'll tell you what's going to happen. So I'm going to reopen it. And look what's happening here. All these supports are orange. This is Spanner Tree doing its work right now. You notice where it's green? The devices at the end, because they don't know about Spanner Tree. But everything here is orange. So I'm doing this right now to show you what's happening. This is Spanner Tree taking place. So it's going to be doing its process of sending out updates, saying everybody's a root switch. And then they're going to get the information, the PPD, the information is being sent out. And then they say, okay, you know what? I'm not a root anymore. I will just take whatever is root and then forward that information and add cost. And look what's happening there. It's happened in a few seconds, right? Well, okay, not a few seconds. It took us maybe 30 seconds as I discussed this. If you go back to the video, play it back, you'll notice it takes about maybe 30 seconds or thereabouts, right? So that's how long it takes us to span a tree in this example. And most likely it's a rapid span tree, not just plain span tree, because it rapid has something called alternative ports in there as well. Other slides will have that. You take a look. So what's happening here? It's the network is when everything is orange, those ports are not in a forward state, they're all in blocked. Blocked means no data is transferring. So what that means? That means when your switches are now starting up, everything is blocked, so no data is transferring, which means a few things. If I take a switch and reload it, well, let me just take this guy here. So I'm not going to just reload him. I am actually going to, I'm going to save some settings. Right, so I'm going to do a reload. Right, so it's doing its boot up sequence, etc., etc. Look what's happening here. Yes, the ports are red down. That's fine. This switch here, okay, now it's orange. Look what's happening. Any data is transferring these through this. It's not going to happen. But look what's happening here. Any data that was distribution 02 is also orange. So therefore, switch backbone 1 and backbone 2. There's no way backbone 1 and backbone 2 could communicate with one another. Right? That's because of how Spanner Tree is operating right now. So this is what's happened when the switch went down. Look at that. Switch is back up, but look what's happening. Spanner Tree is checking over learning and stuff. Right, now it's back up. Now we can see some ports can happen. So can backbone 1 connect backbone 2? Well, we'll just trace links that are all green on both sides, right? So yes, it's going up to distribution 1, and then it's going down to distribution 2, distribution 1 switch, and then going back to backbone 2. So there is communication between it, and it's going through the switch. When we did the reload, which I just showed you, it went down. This distribution switch net 2 did not redo over the spanning tree, right? So what happened is this switch boot up fast enough that it happened, but there was still network downtime. So this is where spanning tree going to have bad thing. And if you look at this, you see loops all over the place. You're going to see loops here. Anything you see 2 ports connected here, that's like a loop happening here. When you see a good example is down here where you see other loops here. So all these are loops that's happening here. Look, this is a loop here. These 3. I need to pick any tree, you might find a loop here, right? So this 2, the one above, take these 2 below, these 2 on top, right? So you get your loops already happening here. Mere fact of the triangles. Once you see triangles with your switches, you kind of see loops happening. All right, so let's continue. Right, so we're going to identify the root bridge visually and then the command line. Identify the SP spanning tree mode, regular or rapid or PVST. Change root bridge. We have something called manual priority and we have automatic priority. And we'll go through some of these steps and see how it is. And then we're going to set up Ether channel. And remember I told you about Ethernet when you're doing our interface range. This is where interface range can help you a lot as well because of how Ether channel is going to. Right, so we're going to identify the root bridge visually. So this is the thing. Initially, orange ports are most likely in a blocked state, The root switch should have all ports on a forward. This is called designated port. Therefore, look for a switch all ports active. Now, visually, this is in a NetPatic tracer design. Now, in an actual network, you may or may not see this happening. And this is a simple one single VLAN. So if it's more than one VLAN, see, can I do? Right. So if it can do more than VLAN, you might not see orange ports in some switches, and with per VLAN spanning tree, every port, like let's say, could end up having every port here could have ended up being green, because that could have been green for different VLAN. So don't trust visually. Yes, they start with this, but don't trust this. You start with that as an initial, then you say, okay, if it's not looking like how it's supposed to look, then you start to investigate. Even if you're thinking, because there are cases where you can have a one switch, maybe it's edge 01, can end up having all the ports are green here. Why? Because this port could end up being different priority. Naturally, not supposed to, because this guy is going to be he's designated. And he's going to be a block port. Right, so there is a case you're going to end up having where one switch is all green. So of course, in this situation, we have one switch here with all ports in forward and state, and they're all going to be designated ports, right? All active ports. So that is a high chance it is going to be a root switch. So what we're going to look at is the CLI, defined via the CLI, and show the span. We're going to use the show span tree. Let me just. Nine simple commands. Enable and then show span tree. Where we are on, we're going to be edge 01. So edge 01 is this switch down to the lower left hand side here. Right? Enable, and then we do show spanning tree, enter, and then we start to look at the information here. So we have different information coming up. Look at the root ID address. So first you're looking at, you can see a root ID. So there are different blocks of data here. So you have the root ID, and then you have the bridge ID. So bridge ID is the switch itself, its own ID. Remember how we built the ID, right? The ID is the 28 byte or 16-bit priority value, and then the MAC address is the next piece, right? So the root ID is made up of those two information. So the key is these two. So when you look at it there, the root ID is basically priority 3069, and the MAC address is here afterwards. So look at the priority. Now we look at the bridge ID. Bridge ID is for the switch. So if you look at the priority 30,769, which is the same priority value as the root ID priority value, which is great. So guess what's happening with your election process? This is out of the box value. So what it's going to use is going to use the MAC address to do the T value and see who is the root switch or not, root bridge. So they're going to compare who has the lowest MAC address. So this is case here. This address has zeros in front of it, while the other MAC address actually has 00E0. So it actually has some data values in front of the first block. So at this time, we know that this switch edge is not the root bridge. That's 1, 2. You know it's not the root bridge because the root ID here is not matching up the bridge ID here, right? Once you see those two values are different, we're not on a root switch or root bridge, which is fine. That's 1. 2, you look at the root port. So how you can tell what's the root port? We're looking at anything you see on the table below, interface, all the interfaces that are connected. And you'll notice that it's only showing only interfaces that are actually active, quote unquote, active connected. So in this switch, edge 01, you have 5, 1, 2, 3, 4, 5 interfaces active. All the rest are not active, they're not disabled, they're not connected. So going back to the case of what a MAC address table should have. It should only have information about an active port. Any port that is not active is not going to show it up. It's not going to take part in these algorithms. It's going to be because it's just wasting time and resources. So it won't do that. So when you look at these interfaces, you're going to see interface role. You have status and the cost, and you have some priority number, and you have the type. So not do too much on the type, but we'll start the left. So we know the interface values. The role is either designated port, right? DP. You have alternate port. So alternate is something new. This is something called rapid span tree protocol. Uses alternate port, and then you have root port. So you should only have one in the case of this environment, span tree. You should only have one root port in your setup. Remember, if you have more one port, means that there's two ways to get to that switch. Means there's going to be a loop. So we want to cut the loop. That's the purpose. Now we look at the status and you see forwarding, BLK block, and then forwarding. So chances are root port are always in the forwarding state. When it's designated port, it's supposed to be in a forwarding state because it's set to say, okay, well, I'm forwarding. Now, when you look at it, forwarding, these are FF0123, that actually goes out to the down client devices. Gig 01 and gig 02 are the uplink. Right, you notice this lab is not labeled. So now you have to do your own kind of labeling to say, okay, where should I do my labeling? Or where should I put my information to port, right? So that's the case. Right, so we have the alternate. So then the two uplink that is going up, you have the one is alternate, but it's being blocked. And then you have the forward. So either way, it's a blocking port as the orange here. So when you see block, it's supposed to be orange, which means on the other side, that segment, as they say when we're done in these slides on Tuesday, that side will end up having would have been a designated port above. So even though it's alternate blocking, it's designated. Now, rapid span tree has certain protocol where they have something called alternate ports. So an alternate port allows you to should you, and that's what's called rapid as well. In event that this link, which is gig 01 report has failed, the alternate port will automatically PPD will send out, and it should get that alternate port coming back up, and the whole spanning tree wouldn't have to do a real discovery. Right? That's just one interface fails and goes down, then it comes up fast. As opposed to spanning tree doing the whole discovery, everything goes back to origin. That's what the problem is, right? So we don't want that to happen. Right, so that's what alternate port helps it. So we have something called priority numbers. These 1, 2, 3, these values represent the non-priority numbers of the interface. Right, and what they're doing is that higher numbers, so you can see the F fastest and it's a 1 to 3, and then once hit gig, it's going 20 to 6 because this is a 24, most likely a 24 port. And let's do a show. Let's do this. Right, it's a 24 port, so 1 to 24, and then gig 1 and 2 is 25 to 26, right? So that's the number. That was the number here. And we can actually, and this is a priority value for the interface. So we can actually change this priority value for the interface. If you have more line cards in this device, that priority value will be different. It might actually be different, or it might actually just continue running number here. Right, as you can see, port 25, right, gig 1 is actually in the forwarding, while the other port is in the block state. Now it's all a matter of which one, because two of them are going up. If we were to swap it, the lower number most likely will be the better candidate for to become the port, right? Also, it also affects what's happening with the uplink switch as well. Okay, so we just checked it. So what we're going to do, we're going to go to, right, we're going to go to the uplink switch via gig 01. Right, so let's go to the next slide. So the uplink switch is backbone 01. Let's check back the diagram. Right, so backbone 01, we just click on this. CLI. Right. I'll leave the size of font. This is on my laptop. I'm going to share it with you, so you guys should be able to see this part. Show spanning tree. right? So same process. We're looking at the root ID, looking at the address, and we're looking at its own bridge ID. And we're seeing where it is, right? So you're going to see there's again, it's two different values. And it's actually, that means that your root ID is not the switch as well, right? Because the root ID has a different MAC address than the switch itself. So now it's actually a different value. So it's still not the root, which means that your ports are going to be the same style, same setup, right? So look at this. The interfaces are slightly different. So you have gig 1019, 18, and when you look at the priority, similar matching numbers. But gig 101, gig 102, these two here. And if you look at the way how everything is organized, you're seeing some designated as one root port, as of course, as gig 1023. Right? And technically that root port might be going up. That's this one here, it should be, because it's in a forwarding, right? While the other one is in an alternate block state, gig 22. Right, so look at that. 23 is actually in a higher value, but it's actually a port. Right, so that is also determined by the upstream switch. And now we have designated and forwarded. You'll notice the cost here is 4, while the cost in the previous switch, let me just bring that up, type 01. The cost is 19 and 4, because 19 is faster than it, 4 is gig. While in this switch, the other switch, backbone 1, everything is gig, as you can see. So that's just one way you can tell the cost. Now this is the next thing. The cost going up to the root, in this case is 8 from the edge switch. So it has to shoot 4 costs. In this case, 2 ports, which means it's 2 gigabit uplinks happening there. One to the backbone, one backbone to the well distribution. When you come across to the backbone now, you see the cost has gone up to 4. Right, which is great because that means it's just one link, especially when you identify and say, wait, this link is a gigabit, right? You know that's the cost of it. There's only one hub to the root bridge. So that's what you use to investigate how far you are away from getting there. And then we look at now we see the uplink port is 23. And we're gonna follow who's connected to 23, which is basically right, let me just say go to uplink switch via 23. Let's go back to tracer. And we see who's 23. I just mouse over now. This is 23 because it's the only one that's active. One in our diagram. Now they have other 2 is active, but they're not. Right, 18, 19. So let's see who's 18, 19. The designated forwarding, right? But they're not root. So yes, they're forwarding, which is great. They're designated, but they're not root. So that you don't follow that path. You could follow it, but that might take you down the tree as opposed to going back up the tree. All right, so let's follow. Next one is the distribution switch. 01. Yeah. All right, so we're gonna just connect and then we're gonna shoot. Right, so you have some questions here coming up. Just right, show spanner tree. You look at the root ID, address 00, right? 997, great. And look at the bridge ID 000C499897. Okay, so the priority is the same, the address is the same. So this is supposed to be the root bridge, right? Right, and they're kind of making it straightforward. This bridge is the root. So you're seeing that. Now, if the other systems may not say that, most switches will tell you that because it's like, yeah, it's either it is or not. It makes it easy to identify. Look how much switches we went through. This is the third one. So if we did not look for this, might find it. Good way to run a script too. So you can actually run a script and look for the word bridge is root. And if whoever has it, especially with your output, you can just do a parsing of the output and tell it identify switches. Look it up. If you have to do over a rediscovery and stuff, it'll pick up something else. You can just rerun the command and it'll tell you who's root. Right, so this bridge root, and yeah, that's it. So what's happening? All ports in a forwarding state, as you can see, designate ports all in forwarding state, all are cost 4 because they're all gigabit. If there was any fast Ethernet or 10 meg links, you would see the cost would change. Right, so we look at the root ID, look at the root port, all ports, and then we have identified root switch. Right, why is it the root switch? Right, so we look at this, identify the. So why is it root switch? Right, the main reason because of the election process is the bridge ID is well, in case the root ID and bridge ID is the same, and even out of the boot, if it boots out of the box, out standalone, it itself will become a root switch. So, and that's why it becomes root switch, because bridge ID is the same. And in this case, it's the lowest value in all the switches in this design as spanning tree network. Right. So what I mean lowest value is the memory bit priority is the same. So what's happening is that the MAC address is the lowest value. So because the MAC address is the lowest in the election process and all the PDU updates, that's why it becomes the root switch. Right. So moving on. Right. So now we can identify the STP mode. Right. So we just doing show span, which we did, and we just identifying span training protocol inside Tripoli. Right, so let's check it out. Let's see. I'm gonna pick any switch actually. So let's go across the side. Right. Enable protocol. Let's bring this back up, right? Right, so the timer is 2 seconds. Actually, it's 20 seconds. Supposed to have a 20. Right, max gauge is 10 times set hello time. That's spanning tree style. That's what you do. You can't change this, but in most environments, you do need to change it. If you have a lot of higher switches being changed up or switches actually being rebooted often, and it's causing spanning tree to reload, then you may have to change some of these values between the edges of switches. Maybe you reduce the age out faster. So your 2 second will go down to 1, and maybe the max age is going to go down to 10 seconds. Right, now we're going to issue the show running config. Right, what we're looking for, anything with spanning tree, fine. Right, spanning tree mode, PVSC. Right, so the spanning tree is for each VLAN, so PVSC. So they call per VLAN spanning tree protocol, but the main STP algorithm is the same. So PVSC is per VLANs. Right, per VLAN spanning tree. That's basically what the PV star. So every VLAN has its own spanning tree. Now that's why we had to do VLANs first. Right, so we're going to change the root bridge, and we're going to set a manual priority. Right, so how do we change root bridge? We're going to actually drop the fastest way is to drop the priority. We can't really change the MAC address. What we can change is the priority. Right, so this is basically it here. Let me go to F01. I'm leaving this up here instead of the PowerPoint behind, because I need to show you what's happening when you start changes, right? Six. Let me just move this slide. All right, so you have the command there. Configure terminal, spanning tree, VLAN, do different ranges of VLANs. So you can do VLAN 1. So our default, if you have more than one VLAN, you can change it. Then we're going to set priority. I'm going to set a value of 4096. Right now, I just want to look at the packet tracer as you do this, and this is what's going to happen, right? Right, something's happened here. The port has changed. It's going to do more learning. And it went pretty fast. Look what's happening here. Remember, all greens was distribution 01, and it's changed. As far as it's concerned, any traffic flow in here is stopped. If you look at it, orange means blocked. Look at this guy, orange is blocked as well. Between backbone and distribution is blocked. So there's a whole lot of block ports happening here, while spanning trees is relearning. Right, just because we changed priority. Now we have to wait a bit because we could do show. Right, this bridge is root, right? Right, so now finally it did some learning. Look at that, we got it in time. So we have a 1 port gig 01 was in a learning state, LRM. All right, so we have listening learning. If I had to change again, I did show span fast, I would have seen a listening, LS or something like that. All right, so now it's a learning. If I do show span again, now it's on a forwarding state. All ports now has changed to designated ports. Well, it was like that before. See if I got further. I see. Yeah. Remember, there are two alternators, alternator route. Designated. Now it's just changed. So now H01 is now the root switch, because I said this is the root. Well, what ended up happening when we did that change is that the links in this network changed when some of them went into this into learning states. Means that nothing is blocked and is not sending information. Means that whatever information that was being transferred has changed. Now, I could try a ping operation and we can see what happens when we do that, right? So let me see if I can do this now. I'm gonna do this. See how we I can do this. CSP, nice. So let's see who we could pick. 110. All right. I tried to ping 10,000 times. So we're going pinging good. Right, so how do we deal with the priority? We change priority. So let's try, how do we fix this? There's a chance you could actually do a no in front. Span tree VLAN. Right. There's a chance. then uh, all right, there it is. All right, there it is. So now we get a timeout. Let's see how long. Okay, so timeout didn't happen too long. About three things. There's about a little more than three. Each one is 10 seconds or so. Tens or 5 seconds thing timeout. And look at this, the distribution is back into what it was before. So let's let it redo it. But the screenshot span tree, right? So it's back to the import so it was before. Let's rerun this span tree. So I just took off the amount, so I just put it back on. Right, spanning tree is going to happen again, right? Things start to change. One timeout. Timeouts. Timeouts. Should start to go on now. 4 timeouts. Well, this guy is more timeouts happening. Right, so look what happened. We changed the route, and now communication across this is gone. Internally, it might continue working, but communication across the core is gone. So imagine you have 10 gig or 20 gig or 100 gig going behind. And all of a sudden, somebody decide to become, it has to rediscover. That's a lot of 10 gig that bandwidth that's lost there, right? In terms of time and timing out. So anything you're copying, that's going to be delayed, right? So that took us maybe almost a minute. 5, 10, 15, 20. About a minute, yeah. And now it's back up. So everything went back to what it was. This I just come here. So if you do show spanning tree, and we get some values coming up, right? Bring up the edge. Notice the changes. So we set the priority. Right, we set the priority. 1496 we said, right? Right, but look what happened here. Priority is 1497, the actual value. When and the reason why I'm being is because of the VLAN number. So you realize one thing: priority values are kind of based on the VLAN number involved in it. So that's why it's in terms of the power. So there's about 12 bits in the VLAN. Goes up to VLAN converter. Basically like this value 49.6. That's the extended VLANs, VLAN IDs. And yeah, actually could do that. Power suite 4096. Right? Plug it in. So to the power 12 is 4096. So that's how much, well, not 4096 exact VLANs, but that's how much the VLAN ID is made up of. The VLAN ID is made up of 12 bits. So for each VLAN, apparently you can have a range of when you set a parity, that is for every single VLAN that's member has bits. So when we do a parity 4096 for VLAN 1, it's going to be 4097 as parity value. If you do a parity of 4096 for VLAN 2, you're going to have 4098 to be parity value for VLAN 2. And you're going to, and that's what we did. We did for VLAN, show span for VLAN 1. So if we look at the output, all right, 4097. If we have another VLAN in this switch, you'll see another spanning tree value. And when we started to VLANs, we got another VLAN in this environment, you will see that happening. You can start with that. Right? MAC address of edge 1, which you just did, I showed that already, and all ports and forward and state. Right. Right, so we just did already, and we're going to do 2. I didn't know, just to show you what happens with the network power change. So let's go back to one. And we can bring back our pinging here. Show what's happening, right? So we didn't know. Okay. Right. So remove it. Let me try to do show. Right, it still doesn't forward in, so we'll see what happens. It's supposed to be in a right there it is. Listening, right? I showed you listening, remember I told you listening, right? So now it's going to change to learning. Still listening. Some are forwarding in block states. So it's transition, you get a timeout happening here. So I'm just going to keep many command because until listening change to learning. There it is, learning. LSN, right? And LRN, learning. I ping this up so everybody, you'll have a bunch of forwarding, root port, block port. Somebody's still listening and learning, right? Right, now it's forwarded. And this is the network stabilizing. So we removed it. Right? And yeah, that's it. So we did this and we actually changed priority and stuff like that. Right, we set priority. Good. View the priority when it's view the show spanning tree. Back to the default. Let's see. Right? 32769. But it should have been 32768 plus 1 because it's VLAN 1. Check. If it's VLAN 2, you'll see another block of text. All of this, guys. And you'll still label have another one with VLAN 002. Right? Again, after just of distribution 01 is root, and one port is port. Right? So that's this guy here. Right, so now we're going to change root bridge to automatic priority. So this is something that we would normally, it's more like, not, it works, but I'm going to demonstrate to you why it maybe not be the best way to do change any automatic priority. All right, so this time we're going to connect the Edge 02 switch. That's on this side, right-hand side. Right, usual process, enable switch by 3. Nothing new, nothing normal or three normal. Test the pause, report updates. We need to start. So now we're going to use something called spanning tree VLAN 1 primary. That's what we change it. Let's bring this back up so you guys can see what's happening here, and then I'll PC ping it away. So indicative. This is a nice way to indicate if your network is changing, right? So you have something monitoring in the back end. Normally, that's what we do when we make changes to systems. We would have some devices pinging and monitoring. A nice tool. I will update that on my tips for your career and stuff. I'll put some software that you can use for monitoring and stuff, some free ones. I'm using something called Zabbix is a nice one. It's open source, Linux style. Problem, it's a little difficult to configure, but when it's working and it's logging, which works really pretty well. It might not do SNMPs, network management protocol, using MIB values. Those are MIB values is what they use to special codes that they use to read information out of equipment. So if something is Simple Informatic Pro SNMP standardized, has certain MIP values, you can tell the Zabbix to read that information. It'll give you statuses. So like CPU usage, bandwidth of our interface, uptime, all that could be MIP values. So normally you'll want to read everything, and then you tell Zabbix to log all and log down or something to save on space. But anyhow, well, I'll put that up later. See how it goes. So now we're gonna do spanning tree VLAN 1 root primary. So config T. If you're not so sure, like I said, remember in the exam, you do spanning tree, you could do question mark at the end. Right, and you have different things. Mode. But you try mode. You ain't touching mode so much, right? PBST or PBST. So right now we on, I think it's PBST. So we're not touching mode. You have port fast. Right, so we could enable PPU guard on the switch. Well, we can talk about PPU guard as well. Right, so we were looking at span tree VLAN. And in this case, VLAN 1. And you're going to do root. So remember we did priority before. We set a value, right? Right, but what we're looking at is VLAN 1. And you can do root primary and root secondary. Primary, there's nothing else after that. So span tree VLAN 1 primary. Enter. And I'll do so. Right, we have some listening states going on here. We have timeout happening here. Our network is changing. Right now, some things are learning, but remember, everything has to go into what's right. So more learning here, listening there. And again, our PC, our data has been interrupted. Our nice 10 gig data synchronization between two sites is now disrupted. So I'm just telling you what you should care for when you do in Spanish. There was a nice something happened. I think when it happened, it was maybe a few months ago. We had a switch port was going into block state, and it keep going blocked, and we trying to figure out why. One of the engineers say, "Well, Spanish is doing what it does. It's doing, right? It's blocking the port. Why? Because it picked up a loop, and it so it's not even doing this kind of thing. So it is only down localized to one switch, but there was some services behind it, so it was affecting certain things. I wouldn't go into much detail about that. And it was in a block state. And when we went on, I think the engineer was shutting down the port to reset it, bring it back up. Spanish started to over listening therein, and then block it down again. So it was doing what it does. So we had to end up physically going to the equipment. So remember, Spanish can only go tell you what's happening. You physically have to go to the equipment and find out what's really causing that. And there was a loop. It was literally there, that device connected to ports, a fiber and a UTP. So that's what happened. So what happened? The fiber was up and current is normal, but the UTP was all connected and it's on the same VLAN. And that's what ended up happening. So it ended up causing a block, and we had to end up fixing that problem. So what we do, we just reset the or the UTP, reset configurations, as in connections, not the configuration, and then solve that issue. Problem was that what we find was weird was that why it started to happen all of a sudden when it was like that before, right? So anyhow, so this happened. So it could be failing equipment, and all that is part of diagnostics and stuff. Right, so root primary, we set it. We did hit here. And then we did a show spanning tree. And we just look, I didn't go into detail with show spanning tree, but let's take a look. Right, we're all forwarding. What we're looking at, we notice some things. The priority is 24,577. And the bridge is the root, right? Yeah, the priority is lower than everybody else. The default is 32,000, right? But if you do this, how do you get 24,577? You basically 32, 7, 16, 8, and I could run the calculator and show you. Right. 768 minus 24, 577, 8191, which is close to 8192, right? So the value went down by about two blocks, right? So it's assuming like it was 4096 by 2. So that's what it did. Now, all ports and forward port, everything else went steady. The only thing different here when you set that, use that command, is that it actually forced it down. It did it in increments. It didn't actually drop it down to 4096, 0.97 as a manual priority. Right? And I will show you something else as we go later on. What's happening because of this. Right, so set up trunk interfaces between the distribution switches. So we'll deal with this pantry a little later about our priority, but we just set it and we're going to continue. Set up trunk in between distribution switches. Right, so it's started the interface range, or trunk, and the encapsulation, right? This happens because of the layer 3 switch. So we need to set the trunk and encapsulation. And that's what's happening here. So let's go. That is distribution. 21, 22, 23, 24, right? So that's these 4 ports here. Enable, configure terminal, is range, right? Gigabit. We go back to my power ports, guys. Let's see. Yeah. 1/0/21. Port speed is 24. Enter. There's our reach. Of course, if you don't know what's happening, what you can do, set a description, right? So let's do a to show its status. There's no name set up for descriptions, right? So let's see if we have a correct range, right? Set a description to trunk 01. And we run it to show again. Look at it, 21, 20, 24. So we know this is the selected range. Very nice tip to do. Right, now we're doing switch port mode trunk. It's okay. Trunk. What's that? Encapsulation. Right, you'll see allowed and native is most of them, but these switches, layer 3, you'll see encapsulation the next option. Right? .1 queue, there's only one .1, there's one trunk and type. All right, okay, so it chopped me out right back out. So what we're going to do, we're going to actually go back and do phase range. From right. Right, so the trunk here. Good. We just go back up and make sure, right? So look at that. We didn't do it yet. VLAN 1, and then we did the trunk. I think it should have done the encapsulation first. Might show up an error. Really package through solution. It should not have shown the error. Did it here. Good. So now we're done here. We can do an end. right? So it threw an error here. Did the encapsulation and then we did this error. But look what happened when we tried it on this switch, it changed. That's a screenshot. Switch port mode trunk. LAN protocol, so that's fine. And then it changed to up, went on up. So this command now worked. So what you have seen, so this is the thing. That's why screenshots are important. So when I did this package some time before, and we did this switch port mode trunk, it gave an error. And then I had to set the encapsulator first, and then I had to set the trunk. But now the new packet tracer, the iOS, when I did the command switch mode trunk, it worked. Right now, in the real world, yes, that's what's supposed to happen. But packet tracer was old version. I'm keeping the screenshot, and that's why I have two sets of commands in the PowerPoint, right? Set the trunk. The only problem is that when I did the encapsulation, it threw me back out into this it was right, there it is. Threw me back out of the interface range because it already was in a trunk. We didn't need to set it. Right, so then I had to go back and do the range trunk. We did it. And this is just some notes to note with the equipment. Once you know what you're doing, it doesn't matter what happens to the iOS. Normally it's reading releases and see if that's what it did. Once you check that, you know what you're doing, you know how to get a configuration. Okay, so you can know what was doing, this is expected. That's what's up. All right, so that's next. So now you're gonna set it up with distribution node 2. All right, just a little word note here, guys. Yeah, no break because we cannot do this online. So you guys can take your break whenever you want, right? So I'm going to go through all the way down to the end. Yeah, should have nobody in now. Right, so we're going to go to distribution 02. So we did that, we set all the ports to trunk. Now we have to repeat it. Look what happened here. It's a post throw, right there it is. Consistent port type. That's because it's not trunk, it's sending non-tag traffic while the other one is sending tag. This is right, not part. Interface range. 1/0/21. I'm doing space 24, but as it depends. I'm going to show you again how to select ranges, right? So you've got our range. They'll show into status. Oh, it's already set for me. That's okay. Well, this is not supposed to happen. Let's see. All right, let's continue. Right, let's change here. .1q. Right, it threw me out. That's fine. Let's go back into my range. Right, let's spin this. I think just throwing up that error because it's port type. Yeah, this we'll leave it out just now. So it was doing port type. Right. Right, did the range, mode. This is different from what we did. When we did this, it's also different. Right? So this time it allowed us to run the first command good, and then the second time run this run. So end of section 1. Now we'll take the break, but we're going to continue. All right, so we did some trunk stuff, and now we're going to set up something called etchr. So you'll notice one thing is that even though we did the trunk, that's fine. We're still seeing some spanning tree thing happening here. Right, so what we want to is to have some high bandwidth going on here. So what etchr does is that allows us to take these links and bundle it into one larger link. The good thing is that you ask yourself, well, how does it work? Why does it work like this? It's because it's sending frames. Let me just go back to, yeah, that's it here. Right, so how does it work? It's actually sending frames. So actually, you know what I can do. So how it works, instead of sending frames individually, remember frames, I switched the switch interface. You know what, let me just I'll clip this, throw it up into my in my PowerPoint, and we could do some diagramming of it, right? A little blurry, but nice. So what's happening is that normally all these are blocking state right now, right? All blocking, but that's fine. What we're going to do is that, assuming that one of them is green, what we do, it'll take a frame and then send it across a link back to this end, right? So that's one frame. Because it's the communication between these two, about maybe, let's say 100 meters, say it's 190 meters to be safe. The cable length is like 90 meters. So technically, the time, let's say this is T0, the time for that frame to reach out there, let's call it T 1.1, the time taken for that frame to reach. Now, if we were to have the other link do the same thing, we could do a T0, the frame is going on a link, coming back on the other side, and it's going to be a T, what? I'm going to put 1.2. Right? That time difference, the 1.1 and the 0.2, 0.1 and the 0.2, this can actually be about less than a 1, maybe less than 1 millisecond, depending. Right? That is basically the time taken. It might be about 1, it could be about 1 or so. I'm just saying 1 because that's a high chance it will be 1 because of the that difference. So because it's coming in like that coming in that's fast, the distance, I can actually, and let me just change a switch can say, hey, you know what? If I could send it on one link and it's taking such a short space, I could send it. When I have 2 frames to send. So let's just put it across here. Let me do diagram. So I could do frame 1 and frame 2. And he is going on one link. And this guy is going on another link. And what's happening? That frame, those 2 frames can be assembled together in one TCP packet. Now, even if frame 2 comes at a different time, let's say frame 2 comes in earlier, that might actually be T1.1, and then frame 2 comes in at T1.2, very short. The buffer size in the Swiss system, and this is how TCP works, even if it goes across, TCP will still reassemble it in frame 1, frame 2. right? TCP segments. That's how it looks. So if you take an initial TCP here, you break it down into 2 frames. Remember, TCP is not doing this work, all right? This switch is doing this work, right? Remember, it's layer 2 stuff happening here. So layer 2. So it's taking it, breaking it up, send it across 2 different links, bring it across the other side and assemble it. Essentially, this is where Ether channel comes in. Basically, that's it. So next, you ask yourself the next question. If I can send 2 frames on 2 different links, and it takes the same time to reach on the other side, therefore I can double my throughput. That's what happened there. I double my throughput. If I have another link, 3 links, I will triple my throughut. 4th link, quadruple my throughput. Why? Because I'm getting these 4 frames on the other side more or less the same time. Your switch will have a buffer to handle that and then forward out those frames where it has to go, right? And its TCP will then reassemble them in the order. This is what Ether channel use does, and there's something called logical a lag or port aggregation, PAGP. Port aggregation protocol is used for non-Cisco related. So this is a standard that can be used by other vendors. So Cisco and Huawei can work with this port aggregation protocol. All right, so this whole thing of Ether channel is basically called port aggregation. And the cool thing about port aggregation is that if a link has to go down, so I'll just put the next red here. If a link goes down, it's simple. It just, the bandwidth drops, but you still have frames still going through the other links as normal. The data, when a link goes down, the amount of data you lost, is the t equal 0.1, 0.2, and it's very small milliseconds. It's only that amount of data if lost on the link. So chance is for you to experiment. Ping operation, small amount of data will fine, but if it's high amounts of data and the link goes down, the systems, your device at TCP level has to plan for that and then ask for a resend of those segments. Right? So you resend the segment, send the frame, and you're going down that line, right? So that's why you could afford to have that kind of drop now. Which means what? Means that you can have a link go down. Your bandwidth could just get reduced, but you're still going to get connectivity going through. And then you have several words point. A link will go down because if all of them bundle in the same fiber, well, yes, that could happen, but your port could fail on that switch as well. And if it fails, they have the other ports to handle it, right? So this is really basically redundant. It's going to basically handle that level of failure and at the same time allow you to go to bandwidth. So this is where Ether channel really comes in and really does a good job. Right? You guys could read up more about that channel later on, but it's really nice to set up. Based on the design, it's only works well between switch to switch. In that way, you can't really span around. What with this environment, this setup you're seeing here, everything, what's this 2 links going to at least, let's say more than 1 link going to a switch, and it can handle Ether channel. Best maybe to set up Ether channel. And when we set up, you'll see what's going to happen. It's good, right? So set up a channel between distribution switches, right? The phase range is seeing what happened here, more trunk and calculation, but we did this already. Right. This is where the real part is. The whole channel one. You're going to set that up on the Ether channel, right? So we're going to go there. This is distribution 1 switch, right? Has to be done on both switches. Oh, I went to get this is my range, right? You must do the range. its range. Gigabit Ethernet 1/0/21. This time I'm going to do space, pick it up. Naturally, when you do at the channel, you should always try to set up in trunk mode, right? Because you want to put some only VLANs in those. Right, so I'm going to go to the commands that will just throw me out. So I'm going to continue. I'm going to do child group. Take it. There it is. I don't know why it's not up. Okay, that's what I'm saying. Same child protocol, right? Child group. It has a range of group numbers. In this case, we do 1. Right, so there's an interesting thing here. You have something called LACP and PAGP. So you have LACP, which is Link Migration Control Protocol, and that's Cisco. And then you have PAGP, which is Port Aggregation Protocol, and that is non-Cisco or more like vendor agnostics kind of protocol. So you ideally will want to use PAGP as your stuff. And then you have the LACP, is more like Cisco. So if you have Cisco shop, like in UV right now, you would use channel group 1 mode on because you want to enable at channel only. Right now, there are different combinations here. You have on, active, passive. So anything you see LACP, so at the channel is part of LACP, and a passive is part of LACP. So it's on, active, passive, and that will come up in the Cisco exam. So tell you, okay, I'm doing this command, what's happening here? And then you have to know, hey, PGP is happening, or you're enabling at the channel on this thing, or you're doing whatever. So it'll tell you, this is what I'm doing, what's happening here. Right? It'll give you a command, and then you can ask you what is going to happen. So it's only through learning it and then experience. That's why you need to know this. Right? So they have combinations. So I'll just go through summary here. If you're doing setting one interface side as on, then the other side is supposed to be in like an active state for it to come on in that way. It depends on the combination. They have a nice little matrix. So if it's active and active on both sides, the port will go into channel mode. If it's active on one side, passive on one side, it'll be going to channel mode. If it's passive, it would not go into channel mode. So the question is, why would you want to have something to go into channel when it's in an active or active passive mode, right? So that's why you would want to kind of put it on. Your billing is designed, you want a channel, put it on. So try to, if it does not work after a while, then something's wrong with that, right? So the channel mode on, window on. So I wouldn't digress too much, right? And show IEP interface brief, right? So now it created something called port channel 1. So channel group mode, channel group 1 mode. Once you do channel group 1 and we enter that command and I'm going active or passive and move on, it's going to create a port channel value here, port channel 1. And just like any port, you can apply certain parameters. Now, the good thing about this is that on the port, you apply something that applies to all the member interfaces. Right? Let's just do a show interfaces. Right? Port channel 1. Right? You can just question mark range. And we're going to check some things here. It created a MAC address here. Look at this bandwidth. That's 4 gig bandwidth now. Members in this channel, which is what you want to see. And this, and let me tell you, this is what I sometimes use this right now, literally on our equipment to identify what's the current rate here. I sometimes do this. Let me see. Can I do a filter on this thing? Right there. So what I would do, I would normally do this port channel 1, I read. So I is include, it's our regular expression, 2, and then you put the word rate. So anything with the word rate any line here, this whole list, and I'm looking at the rate here, it's going to show me the input rate and output rate. The second. I use this to determine how much bandwidth is going on across on that port channel. And those 4 links. When I do site replication, I get up sometimes 18 gigabits per second rates, right? So it's, and I use that to monitor. Engineers use other ports to monitor across the campus. So we have different things happening. Right now, 0 packets, but if I'm doing high bandwidth stuff, I will use this to monitor easily, and then I just take screenshots and I go with that. Right. I mean, they have their own login systems and stuff, but if I need to find out immediately, now, 10 seconds, this will help. Really cool. All right, so show interface is port channel 1. That's what it is. Right, state up. That's all. And this is all the other data. This is the output data, right? And then I use the I rate to find out what's my bandwidth. And then, of course, you check for your errors, if there is any. All right, now we have to set up on the other side, distribution 02. And look at that, where ports started colors change, yeah? Some of these went from forward in here. So let's see what happened here. Face range, gigabit Ethernet, 1/0/21 to 24, right? Do this report mode truck. I do that just to make sure, but I am not ready to end up Q text, so I might have to scratch it out. Ready, dear. It's weird how I did this. Like, see, when I do channel and tab, it's not filling out, but if I do a question mark, it's true. Right? Everything is not filling because there's 2 possibilities. So it's channel group now, it'll fill. Now, this is interesting. Channel group 1 on a second switch, you don't even have to use the number 1. You can use another number. But to be consistent, you want to keep to the same number. In our environment, we have swamp switches with channel group 100 or something, while another one is like 150, while one is 120. But we have a keyword to know why it's 150 versus 120 or something like that. So that way we know that, hey, this channel group is supposed to be belong to this network or this device it interfaces with. And that's what we do. So channel group 1 mode on, state up, then we could do an N. Show IP brief. Right, so there's a port channel here, which is good. Show interfaces, port channel 1. Anything else? Status team, nothing much. Right, and we see our interfaces is here. Bandwidth is 4 gigs. Look, we have a half duplex here. We'll have to see how to sort this out, right? Actually, we can check that out. We can fix that. Let's see. Interface. Port channel 1. Let's try duplex 4. Right? Command that will fiber interface. So fiber is half duplex. In this situation, right? If it's Ethernet, it will be. So you realize some protocols, Ethernet has different sub protocols, right? It's Ethernet, but the physical layer is different. So it's going to have half duplex. Now, just remember, some new modern switches, if you do the package in a GNS3, might allow you to do duplex full on fiber. Right, back to a diagram. Unfortunately, it has gone back to the state. So what we're gonna do, we're gonna try to force this in a way to make sure the links actually we want to get the links going back and forth properly. We'll do that check out in a while. Right, we didn't do this scratch this off. Right, get a bandwidth. Unfortunately, saying duplex half by 2041. Right, do your checks here, and then you have it all. Right, set port channel to trunk. Did I do that? I can't remember. We'll find out. I think I did. Set port trunk. Right, let's do a shot. Let's not check. Right, I shut down the port channel. All the ports are related to this down. All right, that's already seen here. State up. Search have been set, so I don't know why I'm doing all this. Right, sure, this is port channel 1. Yeah, everything's good. Repeat the same thing in the same thing. Let's do a shot motion. Right, it's no problem. All right, final design. Yeah, the question is the channel working? Right, it's set up, but we have to see, right? Because this port isn't blocking. We have to find a way how to fix this blocking state. It's kind of not part of the lab per se, but we'll see. All right, we'll check this out. Distribution 1. Planetary interface port channel 1. Port is in forwarding state. Now we do repeat the process of block state. Right, so we have to fix this problem. Right, so with this 2. Right, so alternate block state. Right, blocking state, notice ports are orange. We want traffic flowing between these two. Right, that changes. Right, block port means we part of the root finish to another link. Indicate that the neighbor distribution switch 01 is not the root bridge. Maybe because it's supposed to be root port and forwarding, right? This guy should have been forwarding a forwarding port, right? If it's root port, it should have been in a green state. So therefore, something is up. Right, so distribution, it should show span. We're doing some troubleshooting here. It's not meeting up with what we expect to happen. So the command show enable show span tree. Right, and we're looking at to see where what's supposed to be. You'll notice that our P0, P01, which is port channel 1, it's an alternate port as block. There's two alternate ports as block, that's fine. Gig 0106 is designated port, it's forwarding, that's good. Gig 103 is root port forwarding, okay, another port designated port forwarding. So you have some greens, you have some oranges, and you can see the oranges on our block is on our port channel, which is what we don't want. Right? We want that guy we want that port to be forwarded. Right, so the root port is gig 103. This links to back 102. Let's just verify that. Back to the diagram. Right, I mean also. Right, it sees gig 104 above here. No? Gig 103. That's going to back. So that's what span tree is telling us to do. All right, back 102, we're gonna see this command. Enable show spanning tree. We look at the details here. The root port straight away, we don't have to read up this. We can check it, right? So you can see that this is not a bridge, there is somebody else, just okay. But a root port, once you have a port, you're going to see who this pointing to. Right? Gig 101 is where this is a report. We'll follow that as well. Gig 102. Gig 101, right? And he's pointing to the edge 02. So open up edge 2. And we'll repeat this as well. Right? Right? As you can see, all ports are designated ports. That's one indicator as a root. But of course, it's just outright telling you this bridge is a root. And then you check in the ID, and you can see the 24,005, and then the MAC address is the same port. But either way, 24,000 is less than the default. Right? It's the same as the bridge ID. Also look at the priorities currently 1. Priorities. Right, it's not 1. This needs to change. So this would have been a previous screenshot setup. So it's different from what it is when you currently are. So it's not 1, it's actually 24,500, 20,577. I should fix that. Yeah, it needs to change. So we can actually remove priority 1, or we're gonna remove primary. Right, so we're just going to edge 2 and do this. should show the same. Yeah, root and root primary should result in the same. That's my PC playing. Right. Okay. Forward and block. Right. It's already started. Right. So notice this fabricated. Look at this. Oh, this distribution 1 and 2 is now green both sides. Compared to the initial startup when we did lab, remember there was some of them were green. One was green and the rest was orange. Right. Look at it, all green. Why? Because we aggregated all ports. So we did the command. There's now one root port going back to backbone 02. We don't need to trace it. Well, we could trace it if we want. So let's go back one. So now it's changed, right? Something's changed. Alternate port. That's changed now. Big 17. Actually, that's called distribution. Yeah, distribution of 1 is correct. All ports are the same. Ports, same as at this bridge's root. Right, so we're good here. Right, so this is bridge. Now we can do show port channel. Show spotting. Right, you can see the port channel. Designated port. I think yeah, it shows. Yeah, I don't know why we right in S channel is also. The main reason to show this pattern is to show that this port channel is up. Not enough port off. Check distribution route. Right? It's a root port means that it's pointing to the root switch or bridge. It's going to be an forward state. Right? So right, so we could just distribution make automatic root bridge. Spine tree 1 primary. Now, unfortunately, I'm not sure why this doesn't go too well. Right, nothing will change here because it's parity, but look what's happening. That's value. That's what we're looking at. That's good. And we go here, we can see it. Right, this is expected, right? Good. Right, we already did this. Show span is on our forwarded one. This is what we want. Let's do this one. Let's do that again. Not too much change, but this is what we want, right? P01 is forwarded. Right. Let me just, before I continue, so almost done here. Right, so before we continue, I want to show you something here. Now we use this command here we use, right? You think about this, technically we can use this command in edge one and see the edge switch and rerun it again and see what happens. So if I go to edge 2, and we're going to just basically span tree VLAN 1, and what is happening? Let me just put the directly behind so you can see. Right, so this primaries, right? To show span, right? So we actually seen the look at this network change again, because all of a sudden Edge decided to put its own command and make our primary, right? So now it's all forwarded designated ports is listening, and it's all going to be root. So Edge 2 is now root. And look at this value here. The priority has gone now from 24 to 20,481. Come back to distribution 0 to 1 and do the show span. And now we have 20,481. Before it was it was the root. We told it to become the root primary, but now it's not. Another switch said that. So this is this thing about spanning tree in this regard. So what happened is that setting it as spanning tree one primary VLAN one primary is not really a good way in setting up a network, because if another engineer comes and set up another switch, now normally you have procedures and stuff like that. So if you do that, then that somebody is a bad actor, as they call them. There's a bad actor, so you shouldn't be having them doing that. Right, so because of the bad actor, they may do this and force your network design to change. You know, this one happening. What you had a high 10, 40 gig bandwidth or 4 gig bandwidth coming here, it's now gone. You lost that. Now it's going down to a gig. And network has to adjust. So data transfer that's happening is would have dropped packets. So look what happened here. So you don't want somebody to be doing this. Normally they get engineers. I mean, technically I can make changes to the same thing, spanning tree. Any edge switch could do the same thing. That will label it edge. So those who have access to the switch, and that's why it's very important when you lock out the equipment to cabinet, because if you have terminal console access to switch, then you can actually get into the root mode and then start to change and let that switch become your primary. Right. So let's just see how we can fix this. So now we have a Hyper-V hacker kind of happening here. Right? So now we have a do show span. We're going to change it. So now the primary drop again to 16. So he's not root anymore. Right, so these guys are in listening states, powering and stuff, and eventually you get his network to come back up. But look at this downtime going each time. Let me get my PC here. It's supposed to be showing some downtime. Well, let me send. So far, no, right? But look what happened here. Bandwidth is back up. But let's say this person on the other side decided to run the command again. 12,000. Look at that. Let's keep going lower and lower, right? Yeah, I realize, wait, it's 12,000. Look at that. The port bumps out. Look at that. They got disrupted. Primary again. It was in trouble in network, right? 8,000. They're going to go to a value where it's going to be a low, right? Request timeout. Right, I think he's good listening. Which is root, right? So you're supposed to get everything back up to green. Right, so now you're back to green, back to normal, but keep going again. Say I want to be number one. And look what happening. Forcing it to go down again. 4097. So this is the thing. Look at this. Right, he's not the root anymore. It's all this blocking. Now, if I were to show VLAN 1 primary, I think it's going to happen. Priority 1. Lowest level. Right, look what happened there. Went down to priority 1. Now this is supposed to stabilize afterwards. Look at this. You can have a war here in the United States. All this down because why? Right? Layer 2 is doing its all this planetary. Now it's back up. Good. If this edge now decides to do say, hey, let me see if I can get back up in here. Priority 1. Right? So now you're same. So what happened here? Did it change? No, it did not. Why? Answer, why did this not change? If both are priority 1, that's the same. So therefore, what's the next value to determine what's the Vijay MAC address? That's what this value is used here. Right? So 00C49 is smaller than 001. So distribution 1 switch 1 because it has a loose MAC address. Right? So that is why you want to look at your design and see which has loose MAC address. So in the event you have to go to priority 1 and somebody else decides to do priority 1, this switch has loose MAC address and it should end up becoming root. And no matter what this person does on the decided priority, it will never change. So Edge will not be able to become priority. So this is just 1, 2. It is possible for somebody to take another switch, an Edge switch, get one with a lower MAC address value. So it's easy to know MAC address, right? You do the show span, you see, hey, look, your MAC address of this value. I can buy equipment and have a lower MAC address than this. Or better yet, find a way to smooth this, make your building MAC address even smaller. Put it on the network, then set myself as it goes. That's where you have, then you could have that contest happening. And it can end up changing network. So that's why it's very important with span tree, what you're doing and how you plan it out. Right, so going back here. So when you're planning a network, span tree can be designed into your network. It can cripple a network, that happens. So you design it in a network. Span tree is to help with your loops, and you can enable it. What we do in our network is that any IT port, like I'm told you, any port that's not a trunk port, the span tree is set up in a way that if it picks up any span tree, it's going to block it. Shut that port down. So you can't come and plug in a switch into the network. You have to know what you're doing. You need to plan with your SLOs so that they are elected as a root bridge, right? So you put that in there, know what this you need to be. 4 switch should be root bridges between one another. That's what you want. Distribution and next, if there are no other 4 switches, and the last. And set the top of rack switches as a root bridge. The same expansion program is not connected to a switch, right? So PCs will not want to take part in it. You don't want someone to plug in a hub and start making changes. Right, so this is your final design. And channel is working how it should. That's what we want. get your two green high bandwidth 4 gigs coming out here, 4 gigs total, and everything. Right, so you guys can experiment the rest of this. I think it's 148, which is cool. Right, so while I'm here now I can start to do a variation of what our let me see if I can do it. Yeah, man. So it's this and clip. Basically, I just add a new slide here and then adding on something for you. Right. So this is basically group project 3691215 in trees, right? So group project one will have a certain. So these are the groups that's going to get something like this. Spin off. What is that's what this right? And these additional notes, so you guys don't know more about that. So what we're doing is that we're basically making switch blocks. So not just the edge, we're gonna have a switch block set up where we have an edge switch. And inside that edge switch will also have a border. It's going to have a distribution switch as part with that switch block. So you may have more than one edge. So this is a switch block here, and we can have another edge switch here. In fact, in my design, where I want, we'll have another backbone. So this will be a new distribution. This distribution now will change the core. And what's going to happen, you're going to have different sets of networks coming up, right? One will be, and you're going to have, be duplicated. So this is called this switch block one. On this side here, we got switch block two. And guess what? This can be switch block two servers. Right, that's what's going to happen. Not only that, this are going to be layer 3 routing or layer 3 switches, which is unrouted. You're going to have a few of these set up. You're going to have redundancy. And these edges are something called a top of rack. Top of rack switches. So normally a top of rack will be a switch that will be then dedicated to either sub switches here, which then go to certain servers. Now there's going to be another block. There's going to be a firewall block. Right, and that firewall block is going to take you out to the internet. So how traffic flow is going to happen is going to come through the firewall to the core, from the core to another distribution, and then that distribution will route it out to the other devices and then back in. Right, so if internal traffic will happen internally and never touch the firewall. And that's how it works. So that is what group 3 design will look like. You're going to have a few of these set up. Yes, it will be complicated, but you will have to look something like it'll be a visual diagram image or image, and then you have to implement that in GNS tree. Right. So yeah, it's not going to be as easy as the others. The others is more tedious, more stuff to set up. This one will be more design. So I'm pulling this from what Cisco is recommended. I will actually go and get the Cisco content as a CCNP and show you, get a piece of snippets of it and show you where to read about it. That's standard, right? So that's what we're looking at. All right, guys. So we're in 153. And yeah, that's the end of this this lab. Thank you very much. It's online. I'll post this up just now. Yeah, I'll see you guys on Monday. And let me know if the do you for the checks on the forms and see if the network is up and down. System source maybe still be up. So I'll have to find out and see what's going on there. All right, guys, thank you very much, and I will see you on Monday. Any questions? Normally email me, right? Bye bye.